I'm Alexis Madrigal. I'm the editor-in-chief of Fusion, which is an ABC Univision joint venture. I'm a contributing editor at The Atlantic. And sort of germane to this discussion, I wrote a book about the history of green technology called Powering the Dream, the history and promise of green technology. And I just want to provide just a really brief frame for the discussion. Energy issues can be framed in a lot of different ways. The way I see it, or at least the way that I think is helpful for this discussion, is that there's kind of two intertwining problems. The first, of course, is the one that we talk about a lot, which is global warming, climate change, that in the developed world we've built an energy-intensive and carbon-intensive infrastructure that we all use to get around the world and do the things that we want to do, but that causes global scale problems. That's one. The second and less discussed problem is that in the developing world, there's lots of places that actually don't have enough access to energy, whether that's electricity, whether that's heating, whether that's mobility. There are all kinds of things that people in the developing world want to do that they can't do because they don't have consistent and high quality access to energy. So it's really two things that we really need to solve if we're going to solve things for humanity and the globe. One is decarbonizing and bringing down the energy intensity of our infrastructure, and the second part is getting way more energy into the hands of people who don't have enough. And so that makes for a particularly difficult problem set. But we spend a lot of time at ASPEN talking about problems, and one of the nice things about this particular panel is that these are people who are trying to actively develop solutions. You have sitting in front of you incredibly brilliant scientists, engineers who are working on the solutions to the problems that the rest of us like to talk about. Joining me kind of to help me moderate this, actually, in a lot of ways, is Harry Atwater, right here to my left. He's one of the world's leading solar scientists, and his group holds the record for the most efficient flat plate solar cell right now. So why don't I turn it over to you, and you can talk about, he's the director of the Resnick Sustainability Institute, and they give out this set of awards called the Resonate Awards, and I think I'll just turn it over to you, and you can talk about their importance.
So let me say a little bit about the Resonate Awards and sort of the visibility of sustainability, and that's the issue that we're really trying to bring to fore here. We tend to think of the world and the future and our prediction of it as an extrapolation of the present. And that extrapolation of the present often doesn't account for innovation. And innovation is truly disruptive innovation can turn on its head existing preconceived notions of how the world can be conceived. And we think in the area of sustainability about the finite availability of resources, the finite carrying capacity of the Earth. But we really have there are no bounds. There are no physical laws that say there are limits to the capacity to innovate. And we have here today some outstanding innovators. And at Caltech, at the Resnick Sustainability Institute, a couple of years ago, we felt it was our imperative to establish an award, the Resonate Award, to recognize and celebrate these sustainability innovations. We saw, for example, in other areas of human endeavors, for example, human health research, there was ample funding, for example, these Millennium Scholar Awards that were being awarded by Mark Zuckerberg and Yuri Milner, to recognize the advances of human health scientists who were addressing very important human diseases. But what we didn't see was any celebration of the biggest global collective disease that we all suffer from, which is a fundamental inability to come to grips with sustainability. And so our goal was to reward and celebrate and make more visible things that were already becoming evident in the scientific community as being very promising, but were below the radar of public visibility. And so that's really the goal of the awards. And so I'd like to introduce the award winners here. And immediately to my left is Professor Delia Milliron, whose career has spanned government, industry, and academia. She's now a professor at the University of Texas at Austin and is transforming our ability to control energy use in buildings through the use of nanotechnology. Joel Dawson is the CTO of Ada Devices, a early stage startup company, a fabless chip company located in Cambridge, Massachusetts. Joel's an electrical engineer, and he's managed to develop innovative technology that dramatically reduces the amount of power that is used in our wireless communication networks, particularly the cellular base stations and the handsets that, you know, when your iPhone dies before the end of the day, give you rise to frustration, but they're also collectively a significant source of energy use. And to my further right, Professor Yi Cui from Stanford University. Yi is a pioneer in two areas, in the solar technology field as a material scientist at Stanford, and also a pioneer in developing new material technologies for lightweight electric energy storage or batteries. And he'll tell us a little bit about that. And Mika Jarvinen from Aalto University in Finland. So one of the things you'll see is that the Resonate Awards celebrate a global partnership of scientists. Sustainability is really a global issue. Professor Jarvinen has developed a way to take the waste products from making steel, the slag that is left over when we've made steel, and to transform that into a useful industrial product that's used, for example, in cement and paper making. So taking literally carbon dioxide and waste products from steel and making them into useful products. And then finally, not joining us on stage, but here in the audience is Dr. Tsoma Iruoi, who is a pioneer from Japan in the area of regenerative fuel cells, making fuel cells that can deliver energy for a hydrogen fuel cell vehicle, for example, and can also generate that hydrogen by running backwards. A very challenging scientific problem.
So who should we start out with? I think what we're going to do is we're going to have each of the innovators just describe their work a little bit to us in, you know, layperson's terms. Should we start out with you, Delia?
Sure, yeah. Is my microphone on? Yes, okay,
yes.
Good. So I'm working on the challenge of improving building energy efficiency, and specifically, we're developing technologies that can make our windows smarter. So the energy context for this is that we use a huge amount of energy to control heating and lighting in our buildings, and those two factors add up to about 1/4 of the energy used in this country, for example. So it's a very big sink on the demand side of energy. And we could save a lot of that if we more intelligently managed the energy exchange between inside and outside through our windows. And in addition to highly insulating windows, that involves controlling the very powerful energy flux from the sun. So the sun, of course, contributes heat into our buildings, and if we could dynamically manage that heat so that we had it in the winter when we needed it and we rejected it in the summer, and we could do that even on a finer time scale as the weather changed, and also manage the daylight in a similarly intelligent way, we could save a lot of energy. So we have a dynamic window technology that can independently manage heat and light from the sun on demand by flipping a switch on the wall or connecting your windows to a control system.
So I had a couple questions when I was reading about this. How would it actually, because it's a coating of nanoparticles, right? So how do you actually control what the particles are doing on the window?
Yeah, so it is based on nanotechnology, as you mentioned, and those nanocrystals have very special optical properties that can be adjusted by adding or removing charge. And so you would do that by wiring up your windows to a switch on the wall and optimally to a whole building control system that could optimize the overall performance of your windows together with your air conditioning and your lighting and so on.
So there'd be software that would sort of balance out the various factors for maximum
right,
energy
exactly. And you know, sitting in your office or in your home would have the ability to adjust it to your preferences, but the system would have some intelligence to master the energy problem.
Right. Does anyone here have a Nest thermostat? Yeah, this sort of, right? Yeah, so do I. Yeah, sort of seems like the next step in being able to, you know.
Yeah, well, the Nest thermostat controls the devices we have today, but this doesn't.
This is the next evolution.
Right. So that gives us another component to put in the toolbox.
So what about if we were to just look at the window? I mean, we've got that window there. Would it look any different, or is the coating completely transparent?
So the coating's completely transparent and can remain in that way as it controls the amount of heat coming in from the sun. But on demand, it could also tint. So if there's too much glare and you wanted to reduce the light, for example, or if it's a bit gloomy and you'd like to allow as much sunlight in as possible, you would have that control.
Yeah, I think it's one of these fun things too where you get to think about what a window actually is, right? It lets in heat, but it also lets in light, obviously. And being able to, as you put it at breakfast this morning, to decouple how much light and heat you get in is a pretty powerful thing to do for a building. Well, thank you.
Joel, could you tell us a little bit about the work that you're doing on wireless energy management?
Yeah. So my name is Joel Dawson again. I'm the founder and chief technology officer of a small startup company that spun out of work that I was doing when I was a professor at MIT in my research group. And the overall impact, the problem that we go after is that it turns out that the cellular infrastructure is a big consumer of energy, worldwide. The cellular base stations, wind up using up a lot of fossil fuels, in order to kind of maintain the wireless connectivity. And sometimes I have to go backwards a little bit because people, what is a cellular base station? You might wonder sometimes, or maybe you take it for granted now, but this little cell phone that it's just you can hold in your hand, you punch in some numbers, you talk into it, and you can speak to your friend in California, you speak to your friend in Paris. You think, wow, the phone should have to be a lot bigger in order to send a signal that far, and you're correct. You're communicating with a cellular base station that's sort of local. Your voice or your text message or your data gets into the whole kind of global infrastructure that way and pops up on the other end at the proper base station. If you look at our ambition is that our technology would be in every base station, every smartphone in the world, and the sustainability impact there is that if you magically change all the base stations today, that would be the equivalent of taking 7 million cars off the road. Now, it's still a little bit of an abstract problem to you, again, because I've just told you about this cellular base station, which you may or may not have known existed. But you experience a version of this problem yourselves, and that is that with your handset, when you turn on Wi-Fi or when you turn on 4G LTE, these really high data rate connectivity options, your phone gets warm and your battery dies. And what that means, getting warm is kind of an indicator that the electronics inside is running inefficiently. It's drawing energy from the battery, but instead of sending that out as useful energy out over the antenna, it's dissipating heat. What you find is that dissipating heat actually limits Steve Jobs' ability to make a small, elegant, clean-looking device. It actually has to be a certain size in order to dissipate that heat. So we're trying to solve your battery problem. We're trying to keep your laptop from getting warm, when you connect to Wi-Fi in your transatlantic flights, and we're also trying to save the world. So we decided as a panel that the answer to can technology save the world is yes. Don't worry about it.
And it's interesting to note the rate of increase of energy use in computing and communications is double that in the rest of the economy. And so this is a kind of a runaway freight train. We have to come up with more energy efficient electronics, because otherwise it's going to impose significant energy limitations on the total growth of our electronics communication infrastructure.
And it impacts kind of the places like the United States, but also in developing countries. Right? I mean, it's getting kind of diesel fuel to run a base station is a non-trivial thing. So what prevents them from using, say, solar energy today? The energy consumption of the base station is too high, relative to what solar energy can provide today. Now, I know that that's improving, but lowering the power consumption and making that more efficient, also opens up, opportunities to use sustainable energy.
Yeah, and you just see the links between all these different systems, communication, energy, and so on.
Speaking of solar and batteries, so Yi, maybe you can tell us a little bit about how we're going to solve the problem, even if the electronics imposes some power consumption, how we're going to extend the battery life even further.
Well, sounds good. So I'm Yi Cui from Stanford University. So if you are not convinced by what Joe just said, we can save the world. Here's a few more technologies so that can help you to understand. We are very optimistic about saving the world. So my group worked on the two technologies mainly. One of them is about batteries technology. It's about a question we asked already 10 years as a professor at Stanford. can you store 3 times more energy and your given size of the batteries? If you could do that, right, instead of charging up your phone every day, let's do every 3 days, your Tesla car, instead of 250 miles, goes 750 miles. That's a long distance. And at the same time, we want to cut the battery's cost to 1/3. If it's 1/3, everybody can afford a Tesla S model, no problem. So that's the impact we try to make. So in order to do that, it's needed a new technology, the new batteries chemistry innovation. So we were able to identify new chemistry, new material that can store 10 times higher capacity compared to current technology. And part of this technology now is started to get into commercial work, get into the cell phone. Hopefully in the next 5 years to 10 years, you start to see everybody's cell phone start to have some of those innovations coming out of these, either from my lab, maybe from other labs, having a much higher energy density. So if you solve this problem at the same time, you can solve another problem. That is to store a lot of electricity to enable solar cells and wind. We know, sun doesn't shine all the time, and wind doesn't blow all the time, so you need to store the energy. So we try to have low cost enough batteries for doing that. That's another goal. So that's one set of innovation. The second set of innovation is about where you get your electricity and energy from, renewable and low cost. So solar cell in the past 10 years has made a big wave, and the cost is coming down. Our research is trying to be able to harvest more sunlight energy, convert into electricity with high efficiency, yet at the same time, to make the installation easier, instead of very heavy, very thick solar panel, can you make it thinner, flexible, like rolling carpet on your rooftop, so you can reduce installation costs and overall the whole system costs. These two areas has been developed hand in hand in my group. They mutually influence each other, and I'm having fun right there.
Yeah, this is a great example of these two areas where we can really go badly wrong by making predictions about the future by extrapolating from the past. For example, if we were to go back and look at the reports from the International Energy Agency and the U.S. Energy Information Administration from 10 years ago, they would predict that by 2030, the mix of energy supply in the United States and in the world would basically be the same as it was back then in 2005. About 85 to 90% fossil fuels, roughly split between coal, gas, and oil. So last year in the United States, 36% of the new electric generation, and by the way, those 2005 reports predicted less than 1% penetration worldwide and in the United States of solar, wind, and so forth. In the United States last year, 36% of the new installed electrical capacity was in solar energy. So yeah, we need these innovations. They will also, the storage in cheaper batteries is not only important for electric vehicles, it's the thing that will allow us to get past, say, 10 or 15% electric integration into the grid. We know that solar is intermittent. It's intermittent when clouds come over. It's also intermittent because we have nighttime, and if you want to use your cell phone or your computer at night, we have to have a dispatchable source of energy that can supply energy on demand. And solar can't do that by itself. It needs to work hand in hand with storage. So with storage, with cheap storage and cheap solar together, we can really think about displacing really making renewables, zero carbon renewables, be dispatchable in the same way that power plants that we use fossil fuels today are dispatchable. And that can really get us to this, essentially carbon-free economy.
Couple notes. When we talk about reducing the installation costs of solar, that might seem like it's a small task relative to increasing the performance of the solar cells, but it's actually a large percentage of the cost of the total installed system. So that other cost, the balance of system cost, is called all the stuff that's not the panels themselves, actually like an area where people feel like they can wring out a lot more cost out of solar panels without actual breakthroughs in the solar cell technology, like the stuff you're working on. The question I had for you, though, battery tech, like if you look at semiconductors, you look at solar, and you look at sort of their development curves, looking at the falling price or increasing performance, batteries haven't followed exactly that same curve. And I think that oftentimes, we sort of want them to have done that. So what makes batteries so hard? Like, what is it about that actual scientific problem that's more difficult than, semiconductors or solar cells?
This is a very interesting question. I started to work on battery 10 years ago when I joined the Stanford faculty. I also asked myself the question, why battery innovation is so slow? It's so simple, right? It's two electrode, a positive electrode, a negative electrode, electricity back and forth during charge and discharge. We know how to do that, right? Yeah. In reality, that's not true. So batteries inside is not electrons are moving. Ions are moving also. There's a lot of chemical reaction happen inside we don't understand. It's a black box. So it's happening in a very, very slow rate. After I learn more about battery, I feel like lucky. We even can get lithium-ion batteries to work. And thermodynamics tells us it shouldn't work because of instability right there. But kinetically, it's stable. We are lucky to have that product right there.
That's in all the battery that's in all your phones. Yeah.
Actually, I would turn that around a little bit. I think that from my perspective, battery technology has actually improved at the normal rate.
That's good to hear.
What we've seen in microelectronics, kind of doubling the capability every 18 months for decades is insane.
Yeah.
That is nuts. And I cannot think of another example of any technology anywhere in the history of the world where that has happened.
Yeah, so it's a very important point. We are used to the idea that technology lives on a Moore's law curve, that we can reduce the cost and increase the performance by orders of magnitude over time, and that there's an exponential involved in those. So actually, we went back about 6 months ago and looked at some data on the price of oil, the price of photovoltaic panels, and the price and performance of, say, silicon electronics over the last 30 years. So go from 1985 to 2015. What you see is that if you look at, by any measure, the Moore's law reduction in the cost per bit of electronics or the increase in performance for a given area, it's gone, the cost has gone down per bit by 7 orders of magnitude. Amazing.
Yeah.
Incredible.
Factor of 10 million. Question about, what about solar? Solar has actually also gone down exponential curve, but it's not over as many orders of magnitude. It's only 2 orders of magnitude. But 2 orders of magnitude is a lot. That means we went from $75 for a panel to 75 cents for a panel, silicon solar panel that you would put on your roof. Then we also looked at the price of oil. The price of oil in 1985, or actually we have to go back a little bit earlier because there was a reduction in price then, but if you look at it sort of averaged over the last 30 or 40 years, it's about constant. So there is a Moore's law, but it is slower for energy tech.
Which is lightning fast, and we just don't recognize it because we've had this outlier of outliers, in kind of Moore's law. And I think part of that is, it's kind of difficult to understand why that is. Part of it is that silicon itself, which is a material that you hear about, is a miracle of a material when it comes to manufacturing and consistency. And it just so Moore's law benefits from that tremendously. It just in terms of being able to manufacture these things. There's a lot of reasons. There's been a huge community that's been dedicated to this, but we can't get greedy. We cannot expect Moore's law to be happening. Whenever you have exponential growth of any sort, wow.
I think there's also difference in thinking about fundamental limit. When transistor was invented a little bit more than half a century ago, you are in a size like this big. And then your fundamental limit is atomic size. You have 10 orders of magnitudes you can play with, roughly, about 10 orders of magnitude of a different size scale. So you can keep going down towards that limit. But solar cell and battery don't have 10 orders of magnitude as a limit right there. Theoretical energy density for the most highest energy density batteries It's about 10 times of the current technology. That's it. 10 times is the chemical bonding limit. Solar cell efficiency, Harry, we know the limit right there. It's not infinite. Also have a few times room you can play, in a very extreme condition. So it's a different scaling law. The good thing about energy technology, you don't need to have that order of magnitude improvement anymore.
Right.
You only need to cut the cost by half or 1/3. Your efficiency go up, by doubling. For solar cell, you don't even need doubling. So tremendous things will happen.
One way you know you're with scientists and engineers is they say orders of magnitude a lot, right? That's thinking in terms of that.
That's 10 times. Okay.
Yes.
And then a factor of 2 is cutting it in
Yes,
half.
right.
So Alexis, let me also introduce Mika Jarvinen. And so, of course, one of the things we see that's fundamentally different about energy versus information systems is that we have real physicals. We have atoms and chemical bonds that we have to work with. So in the area of manufacturing, for example, manufacturing basic commodity elements like steel, we use tremendous amounts of energy and we produce tremendous amounts of waste. So what can we do about that?
Okay, thank you, Harry. We are working in Aalto University on a process that binds CO2 from, for example, the chimney of the steel plant or power plant, and we bind this or take it away from the atmosphere in that sense and make it a valuable chemical that can be sold later on. And just to give
So
you
you're taking CO2 out of the smokestack of the steel plant.
Yeah, exactly, yes. And to give you just a hint of the magnitude of the magnitude again. So the annual production of steel in the world in every year, it's 1,500 million tons. And if you cast a cube of steel out of that, it's like 0.5 kilometer cube, a big one. But while making that, we also produce a side product or waste called slag, and the mass of that is something like 500 million tons. That's much lighter.
We're producing almost the same cube of waste as we are
I
the
think
steel.
it's even bigger because it's less dense. So it's like a mountain of waste every year. And what we do in our process is that we take this waste slag and we dissolve calcium out of that very effectively. And then we filter this solution and then take the CO2 from the stack or chimney and bubble this through the solution. And what happens, there's a chemical reaction taking place and precipitated calcium carbonate is formed. So in principle, it's like a limestone particles are formed. And
Which is one of the components of cement.
yes, exactly.
Normally takes CO2 emissions to produce, for example.
Yeah, exactly. And paper industry is using a lot of this. So for example, if you have this nice white printing paper, it might have like 1/3 of the mass is this precipitated calcium carbonate. So in our process, we really take something that is considered to be waste previously. We take that, and then we take the
Actually, two forms of waste, both steel slag and CO2 going up to the smokestack.
Yeah, so we are taking these bad things and making a really valuable thing out of those. And at the moment, we are building trying to set up a company on this topic. And the idea is to build like a demo scale plant first. So we have now a pilot plant in Aalto University. So it's like 200 liters reactors, 3 of those. And the next step is we are planning to have like maybe 100 or 1 times bigger reactor. And that will be taken, for example, to a steel mill or to a, for example, PCC, like precipitated calcium carbonate factory, and then test this, that it works in practice. So in order to do so we really need like factories to show that it works.
This is one of the, and this is maybe a great segue, because one of the challenging aspects about all of these technologies is that they involve manufacturing relatively large quantities of things. that requires manufacturing, it requires materials, and that's one of the big challenges in renewable energy. And so finding pathways towards innovative products, but also ones that have a low capital intensity to manufacture is very important.
So they can get, and one of the other, with some of these other CO2 sequestration technologies, how easy do you imagine this is going to be to actually bolt on, as they would say, to a factory?
Well, actually, we have been already thinking about, since we are now setting up the company, so we are thinking about this kind of a container, or sea container basis concept. So we would have like build in like a workshop. We build the small plant into one container, and then this would be transported to, for example, to a steel mill, to the customer, and then it is tested there. So it's like a just tube of CO2, and then like a conveyor of slag.
Slag.
From
So a container, you're thinking like a shipping container you put on
Exactly.
the back of a truck.
Yes, yeah. And then it's like test with first container first, or this plant, and then if it works, we just
Add more containers.
Yes, and we can pile them, and then it's also a good way, so they are like working in parallel. So if there's a maintenance issue, so one container can be taken away from the system and maintained elsewhere and replaced with a new one, or something like this could be. So I think it's our objective is to have this, for example, in steel mills in Finland, and then there's a company called Ecochem they are like treating different kind of waste materials, and they were really interested to build their own pilot plant next to their on site.
Harry, I have a question around the general idea of carbon dioxide sequestration. I don't know if you guys remember 5, 6, 7 years ago, there were a lot of people talking about, well, if the problem is CO2, we should just like take the CO2, maybe we can inject it underground, maybe we can inject it into, caverns or make things out of it, as like we're seeing here. And then I feel like, that ebbed away for a while. From your position sort of at the head of this Sustainability Institute, what have you seen in terms of, did the technologies not work out? Were they just not economical? Did people sort of not care enough because global warming kind of ebbs and flows in terms of how much attention is paid to it? Like, what happened to that?
Well, okay, so there has been technical progress. Demonstration plants for CO2 sequestration have been developed. In fact, one of the lessons we've learned is that the best way to capitalize innovative technology is to ride sort of on the shoulders or stand on the shoulders of an existing technology. And the technology that's currently being studied at pilot plant form for CO2 sequestration is taking CO2, say, out of the flue gas of a power plant smokestack and injecting it underground. And this is actually a process that's used already in the petrochemical and oil industry to do enhanced oil recovery. So they purposely inject CO2 underground to get more oil to come out. So there's quite a lot known about the injection of CO2 into favorable sites where you do this enhanced oil recovery. So that has really been the context for the technology demonstrations that have been performed to date. So the question is, can this scale? Will it actually make an impact in the power plants that we already have? One of the big challenges is that if you take an existing power plant, say a coal-fired power plant in West Virginia or something like that, and you say, I want to sequester the CO2 underground, you've just added cost to that electricity, that coal-fired electricity. Those coal plants right now are struggling to compete against the inexpensive natural gas plants. So really, it's the entire change of our energy mix in the United States that, at least here in this country, has really kind of dampened the appetite for introducing that.
Right, because it used to be
technology.
Before we had a lot of this sort of glut of natural gas, that coal was substantially cheaper than all other power sources. So you could have imagined that you could have stuck that cost in between the delta between the coal and the natural gas and other things. But you're saying that's evaporated.
Yeah, and we also see, for example, just to come back to solar for a moment, for a long time, and in fact the current, a still official objective of the Department of Energy, the so-called Sunshot program announced in 2010 by then Secretary of Energy Steve Chu, was to bring the cost of solar energy made by solar panels down to parity with electricity that's produced by fossil fuels in the grid. It now looks like the basic goals of that Sunshot program are going to be achieved early. The goals were to achieve these goals of 6 cents a kilowatt hour, roughly grid parity by 2020, and it looks like they're going to be achieved in 2017 or 2018. So if we now have solar that's at grid parity, and solar, of course, doesn't produce CO2. It has these other issues related to storage. But now if I have to add 2 or 3 cents a kilowatt hour to capture that CO2 at a coal plant and inject it underground, that doesn't look like a good investment if I'm a utility or running energy generation plants, because I just added cost, and whereas I have other technology options that are now getting cheaper.
Mm-hmm. Let me ask a slightly broader question. The sort of underlying field, or one of the underlying fields of a lot of your work here is material science. Maybe slightly less so for you, Joel, but for everybody else, material science seems to be just the fundamental science at the base. How has material science changed? Because my perception is that it used to be something that you did at like a bench, right? Like you mixed chemicals together and saw what happened. But that seems to have changed a lot. A lot of it now is like computer modeling and being able to take advantage of the tremendous computation abilities that we now have. Can maybe some of you speak to that change? Because I think it's one of those things that, because it's a technology that sits really low down in the sort of technology stack, you don't really see how big the change can be that comes out of improvements in material science.
I can probably start to say a little bit about that. So material science, there's still a lot of bench mixing chemicals that's still happening as before. But in the past 20 years, the nanotechnology development, I think, really changed material science in a dramatic way. So we now know how to make materials the shape we like, with different composition, coming together, forming so-called heterostructures. We can make it a different size. We can put them together a very different way. We have the tools, new type of scientific tool, to really know what happened inside the materials, at the surface, at the interface. So this is now a new time to look at the energy technology, so whether it's a solar cell, is batteries, is window technology, really bring a new capability. We can do a lot more right now. So I was mentioning earlier, battery technology is very hard, but with all these new tools and material science coming in, new capability, now we understood the battery a lot more compared to before. Now it can be the time with the assistance of computer modeling as well. We can design material, design our technology in a much more predictive way. So it's a very, very different time.
I'll add a comment to that also, which is that I think one of the most exciting trends in material science that can positively impact this space is that we have new nanotechnology and chemical methods, especially for reducing the processing cost of materials. So materials traditionally came out of metallurgy and very high temperature, high energy intense processes. So in batteries, for example, the battery in your cell phone uses a graphite electrode, and it's just carbon, and you'd think it would be low cost, but it's actually quite expensive because it's processed at high temperature. So with new methods to make materials that can be done at low temperature and taking advantage of bio-inspired methods and so on, that's really important. So for our window technology, for example, the performance of the window is extremely important, but if we can't make that coating at a sufficiently low cost to get those windows into new buildings in China, for example, where there's an explosion in building going on, our impact on sustainability will be very limited. So that's a very important direction, I think, that materials has developed in.
I think materials will always be an important area to look at, and I see it from kind of a different angle, which is that in microelectronics, what tends to happen is that we make transistors out of different materials. First we'll make it out of we've done it out of gallium arsenide, silicon, germanium. I mean, the actual name doesn't matter so much, but the point is that the material will discover a material with some exciting new property, and then there's a frenzy of design activity to exploit that property. That frenzy of design activity can't really go on forever. After a while, we get it. Okay, this is the best way to design, an amplifier, in this technology. And then either the innovation just sort of stifles, or looking for a new material is a very natural mode of inquiry. What can I do? Can I find a better tool that can make things work?
Why don't we talk? Oh, go ahead. Oh, sorry.
Yeah. So in principle, my group works more on the, let's say, traditional energy processes. So we burn something, and then we have a turbine and things like that. So there also the materials technology plays a huge role, because the efficiency of these processes is the higher the temperature in the process, the higher the efficiency is. And then, of course, for example, the plates of the turbine, they need to resist very high temperatures and very high stresses. And there has been these so-called super steels developed. And for example, the like really high-tech turbine plates are molded so that the single plate is one crystal. So it's like really high-tech, also in that like a more traditional industry.
Why don't we talk about, because we have some solar experts here on the panel, I think there's a lot of questions about that people have, like, how good and how fast can solar technology get? And so why don't we just go to there, like in 5 years or 10 years, something that's close enough that we can really think about it. How good will solar technology be, and what changes will that have in the world?
So I think the figure of merit for goodness probably is cost per watt, cost per power generated, or the total cost for total energy generated during the lifetime of the system. I think there are two areas where there's been huge progress. I mentioned, for example, just a moment ago, that the goals of the original Department of Energy Sunshot program to bring solar electricity on a par with electricity being generated in the grid, originally set as a very ambitious goal 10 years ago, or actually only 5 years ago, for 2020, will be met 2 or 3 years early. So we have to come up with a new goal. So there's been a whole conversation in the solar technology and energy innovation community about what's the new goal for solar energy. What we see actually is that solar is not simply going to come down to the cost of fossil fuel generated electricity and then stay there. It's going to keep on going down. And so how low could it go?
Right.
So, for example, we see first examples of solar installations, solar projects being installed, which are being priced 2 cents below the current average cost of electric power in the grid. So instead of 6 cents a kilowatt hour, the lowest cost solar installations are now being installed at 4 cents a kilowatt hour. That extra 2 cents could be used to pay for Yi's battery, to add the storage capacity to make the solar dispatchable. So now we have a completely level playing field where solar can now expand beyond the limits of it could supply energy to the grid given its intermittent character and be a more dispatchable source. But could we go even further than that? And there are a lot of people, so I was talking with Arun Majumdar the other day, sitting in his office. How far could we go?
Can you tell them who that is?
Arun Majumdar was the founding director of ASPEN.
I've interviewed him before. He's a good guy.
And so he was probably most responsible for the acceleration of innovation within the Obama administration of taking basic science and really bringing it to the marketplace. So that's what ASPEN does. And he sees the possibility that we're going to have electricity that's so cheap, maybe even 2 cents a kilowatt hour, that we have to find other things to do with it. We have to find, so for example, what are the things that we could think about doing with very cheap electricity? We could think about doing desalination of water at a cost competitive basis. That's of course a big issue in California, Southern California, where we're being asked to adopt very dramatic water conservation measures. We could create fuel. For example, we could use electricity and electrolysis to create hydrogen renewably. We could create fertilizers. We could create storage for electric vehicles tremendously inexpensively. So we could actually use electricity in places where we use fossil fuels in basic industries that make chemicals. For example, Dow and ExxonMobil and DuPont and so forth that make specialty and commodity chemicals use a huge amount of fossil fuels in the basic chemical making. We could think about electrifying that.
Yeah. Do you see this as essentially inevitable? Like that now the routes have been identified to get to that kind of pricing and all it is just science and technology kind of cranking away? Or could something happen out there in the world, some unexpected thing that derails, what seems like the progress that's happening? Anybody can answer that?
Well, both Yogi Berra and Niels Bohr wisely opined that predictions are difficult, especially about the future, as I mentioned earlier. So I don't want to say that nothing could derail it, but I think that what you can see is that savvy business people are now starting to bring large amounts of investment into the solar arena, whereas many of them were doubters maybe 4 or 5 years ago. That's a very important signal.
Go ahead.
So I want to add more onto this topic. So we are discussing whether technology can save the future, save the world, right? This is really coming from the angle we are getting into trouble, can we save it? But at the same time, every time you have trouble, that's where opportunity really starts. So Harry mentioned this, the solar electricity cost. We now get to 6 cents per kilowatt hour as competitive as a coal-fired power plant. We can go down further, this indication, this cost is coming down, 4 cents, and Austin, Jeff Boyle is in the audience right there, so just mention that also. Very likely, in a couple of decades, we could get to 2 to 3 cents per kilowatt hour. So Harry mentioned the things you can generate fuels using electricity. You can generate hydrogen. You can generate high-value chemical product. If you think about the whole world in 20, 30 years, or maybe a little bit longer than that, so there's opportunity right there, thinking about industrial revolution we have in the past couple of times. Oftentimes, we're really starting from energy. How do you drive the engine? And this might be the time we think about, what's the next big industrial revolution we can have. I think we are sitting onto an opportunity more than just a problem.
Actually, just another thing for, I think, the general audience. I think the speakers got together this morning, and I think you raised a very interesting point, which is, why are we even talking about cost? Surely there's a moral imperative when it comes to saving the planet, and, I think, what we, just discussed about it, that should be true, but that's sort of not necessarily true. And one of the things to notice, in these things is that in order for technology to really get adopted, it sure helps if it's a business success or a business win. If someone can be profitable, and it shouldn't have to be that way, but it tends to be that way. So we talk about cost and things. I mean, cost it's partially a surrogate. If something's really expensive, that is partially an indicator the technology doesn't work well. But also, these technologies really kind of go mainstream when it's a huge money-making opportunity. And it's a deep question as to why that would have to be, but that tends to be how it is.
Right. What about, in this world that we're imagining where solar costs very little, what else can, the utilities obviously have some major interests in power generating assets, but are there other things that we could imagine really changing about somebody's day-to-day life, or is it just that the electrons they get from the plug are coming from a solar panel instead of from, the grid and a gas power plant?
Yeah, well, I think saving energy, kind of generally, one good example of that is I noticed this morning you were wearing an Apple Watch.
Yes.
And what you've probably noticed is that
it's destroying the battery life of my phone.
Destroying the battery life because the radio is on.
Right.
So,
That's right.
So you think about. Some things, there's a lot of things we could do if we could just sort of throw an endless amount of energy at the problem. Really, what enables a lot of these gadgets, making them really small, so you don't have to store a lot of energy locally, has to do with. So I think, these, and we've obviously gotten a lot better at it. That's why the Apple Watch is sort of possible in the first place. But I think that saving energy, you can exploit in 100 different ways. You can actually save energy, or you can use the same amount of energy and perform better, which tends to be how things go. But having energy efficient, anything, and efficient, high density energy storage, anything, winds up enabling a lot of these small, elegant gadgets that we use.
Delia, let's turn to something much bigger. Let's turn to buildings. I assume that you focused in on windows because that's like a major lever for being able to improve the efficiency of building energy use. But what are the other sort of opportunities that you see or you've thought about in terms of improving buildings' energy efficiency?
Yeah, I'd love to comment on that, and I want to follow up first on this. How does it change the
Yeah.
experience in the world in the
yeah.
context of buildings? And one thing that really inspires me about the windows problem is that changing the paradigm of energy in windows from being net energy problem, which they historically have always been a source of energy and efficiency in buildings, to making them an energy asset for the building, opens up the possibilities for architectural design, for your experience in the space, and so on. So I think it really does have this possibility, the way that we save energy, to revolutionize the way that we think about designing not just our gadgets, but even our
So
infrastructure around
typically,
us.
for example, in a cold climate, the way we save energy in a window with buildings is to make the windows smaller.
Make them smaller, yeah, or brick them up, even better. You know, that used to be the ideal building from an energy perspective, had no windows at all,
Right.
And it's not good for the human psyche, right? There are fundamental gains in experience and productivity and so on to be had by having more engagement with our environment. So window technology that can be energy efficient enables this whole other level of human experience and productivity and so on that, of course, would be tremendous to see become a worldwide thing and not only used in flashy featured buildings that you see going up in places that are very glassy at any energy cost. If we can do that while conserving energy and even improving the energy picture, that's really revolutionary in my mind. But beyond windows, as you mentioned, there are all sorts of other opportunities for technology in buildings. So one thing that I've been following closely is much like solar energy that fluctuates over the course of the day and so on, the heat loads change over the course of every day. And if we could balance that load so that we could keep the building cool during the mid part of the day and then release the heat back out at night when we need that heat, that's a very powerful way to level the energy, basically the way that the building breathes energy in exchange with its environment. So there are materials being developed that are basically nano-encapsulants that store a tremendous amount of thermal energy during the hot part of the day and then naturally release it as the building becomes cool again. So that's another example, and these could be put in your walls. They
So
could
it's
be
sort of
made
like the
transparent and put in your window.
nanotech version of like passive solar.
Yeah, it's a piece of the passive solar problem, exactly.
That's really interesting. Two things I want to touch on. We can do it in either order. We haven't talked a lot about mobility, and by that I mean cars, like transportation. And the second thing I want to talk about is the U.S. versus the developing world. So what do you guys want to do first? Do you want to do?
Well, let's talk a little bit about mobility, because I think one area that we're focused on in mobility is developing, for example, lithium-ion batteries, which we can maybe hope and expect will generate an electric vehicle fleet that can really displace a lot of fuel consumption. But how many of you flew to this conference in an electric-powered airplane? So about 10% of the fuel use in the United States, actually no, it's a little less than 10%, but is in aviation and in long-haul trucking and other areas where it's extremely difficult to displace the fuel use. So what we need is a renewable fuel cycle, something where we take advantage of the fantastic energy storage capacity that liquid hydrocarbon fuels have. For example, if I go to the gas station and I fill up my gas tank, I have a plastic hose that I attach to when I take off the gas cap from my fuel tank and put it there. And when I turn on the pump, I'm pumping the equivalent of 5 megawatts of power through that plastic pipe. So $2 plastic hose that's not $2, but it's 5 megawatts of power going through that while I'm fueling my car. So that's a fantastic energy density. And we can use that fuel to fuel a vehicle that has a range of 300-400 miles. We simply don't have the ability right now to be able to charge vehicles at that rate any charging station you go to, even the fast charging vehicle stations, take more than a few minutes to fuel. And in aviation, we're simply not going to have electric-powered airplanes. So what can we do? We could use biofuels. For example, Boeing is now introducing in some of its flights biofuels, but biofuels don't scale very well. You run into the energy efficiency of producing fuels from biofuels, which is basically taking the products of natural photosynthesis, fermenting crops, creating liquid fuels from the fermented crops. The problem with that is it requires a very large amount of land area. Food competes with fuel use. So can we get out of that conundrum, the competition between fuel and food? So another technology that is emerging is the technology of artificial photosynthesis. So artificial photosynthesis refers to engineering a device that looks in many ways like a solar panel, uses inorganic materials, many of which are found in solar panels, to perform the same functions as a leaf would in a plant, and produces hydrogen or produces liquid hydrocarbon fuels directly from sunlight. So at Caltech, for example, we have a project called, and it's a joint project with the Lawrence Berkeley Labs and Stanford Linear Accelerator Lab, called the Joint Center for Artificial Photosynthesis. So this would be a new technology which would allow us to reach this goal of displacing that very hard to displace part of the energy sector, which is liquid transportation fuels in places where we have a hard time using anything else.
That's interesting.
So yeah, let me add a little bit also. So it's absolutely true for the long distance, those heavy trucking, airplane, shipping in the ocean, in the sea. There's no way it has to be chemical fuels. Now I want to tie together this mobility with solar, with electrical grid. This whole story coming together, really tied up together very nicely. So when renewable electricity is low cost enough, now there is a transmission line, very high voltage, 1 million watt, that can go distance more than 2,000 kilometers, only lose about 5% of the energy, very efficient. And then this chemical fuel synthesis using electricity, low-cost electricity, can make chemical fuels, can charge into the batteries. Now you have very diverse options to also impact mobility.
That's interesting. Let's talk about the US versus the developing world, in part because we're not building a ton of power plants in the United States anymore. We are, one of the reasons that solar has been a large percentage of the generation that we've built here is that we're not building that many big power plants, but we are in other parts of the world. So how are you all thinking about what you're doing as sort of a global problem and addressing global markets, not just the ones here?
I think with the cellular communications, it's kind of easy. We had to take a step back and think about, in the U.S., we had a very well-established communications infrastructure, right? And it went sort of smoothly for us, so it's easy to take for granted. But actually, if you think about laying down a wired network, in a country that is 3,000 miles wide, such that anybody can just pick up a telephone, it's an amazing accomplishment.
Yeah.
And then our
There's literally people just stringing a wire. It's amazing to see those photos. It's like
stringing wires.
Yeah, if you calculate the replacement cost of that, it's over $1 trillion.
I don't know if you can hear that. I don't know if they heard it in your mic.
Okay, yeah. So if you calculate the replacement cost of that, it's over $1 trillion.
Right.
So
in the U.S., what we do to do wireless is basically we kind of we have the wired network and sort of slowly replace it. But if you're a developing country, you don't start by building a wired network. You go straight to the wireless. And that is where now the energy consumption of your wireless network becomes of immediate concern to you. And you can think about it in terms of fossil fuels, the cost of diesel fuel, but there's also kind of other things. We were talking to a network provider at the Mobile World Congress, and one of the things that happens is in some countries they have to have guards at the base stations to keep the diesel fuel from being stolen. So it's I like to say that the problem of energy consumption with communications is kind of hiding in plain sight. I mean, you don't really think about it, but it shows up in so many different ways. And in the developing world, if there's this sort of big drive to build a communications infrastructure, it's directly tied to our ability to have kind of low power base stations that can still have a wide coverage.
Yeah. I was telling Joel earlier that I saw a pretty incredible story about a phone that's been catching on in Accra in Ghana that is basically a huge brick. Like unlike the elegant phones that everyone's carrying around, there's this massive thing. And the reason is that it's actually a phone that you can use. You can just swap out your SIM card from your other phone into there, and then you can use it to charge your main phone. So it's very stripped down. It's just for making calls, text messages, and it's basically just a backup battery for your other phone. And it has caught on because there's intermittent power outages in Accra, and so it's become this way of sort of making your communications like much more resilient. So technology like this in a place where the power grid is going in and out pretty regularly is bringing your power consumption of your phone down is a big deal.
So I'd say for built infrastructure, there's a similar opportunity to get new energy efficiency technologies into those developing markets much more rapidly than what we can do in the United States. So for Windows, we certainly don't replace our Windows all that often. So the primary opportunity for any new efficiency technology becomes new construction. It's much more expensive and much slower to embed things on a replacement basis and a renovation basis. So where you have these explosions of new building and new infrastructure, there's kind of a race underway to get the technologies ready and at sufficiently low cost that they can have a significant presence in those markets while we have that chance, while those markets are exploding the way they are. So that's a very compelling opportunity, and I think in the investment community, a number of people have recognized this. So my startup company is attracting a lot of interest from people familiar with the Asian markets, for example, who are trying to capitalize on that.
Yeah, I think what goes for building efficiency goes double for energy generation. If you look at the places where we're going to have an opportunity to curtail additional rapid growth of CO2 production and greenhouse gas emissions, it's going to be in the most rapidly developing economies. So right now that's in Eastern Asia, Southeast Asia, India, and those are the places where we have to bring the technology solutions, zero carbon energy, storage, building efficiency. If we can't deploy in those countries, arguably at some level, we can affect our own quality of life, our own quality, our sort of sense, our smug sense of self-satisfaction here in the United States, where, by the way, greenhouse gases are actually going down now through energy efficiency and changes in the economy. But in other places in the world, they're going up very sharply.
Yeah, one thing, or important thing we need to consider is that we live in a finite planet, and we have a finite resources of like natural resources. So we all know that, I've heard that the fossil, for example, oil is running out with a certain rate, and for example, such a simple thing as sand, there has been stories that like even sand is like running out. When we build buildings and made cement out of sand, that is, we can't get the sand back. And in my opinion, we should think about like what is waste, and should we get rid of the term waste totally, because I like to think that instead of waste, we have raw materials in that waste, and how to get them back, and because the resources in the nature, they are not infinite. They will run out someday. And I'm thinking about the future generation on the planet. We need to save something for them too. So the recycling and to get rid of the word waste would be something really nice I would like to see.
Or did you want to say something? Or?
Yeah, so your question about energy goes global, I think, has multiple facets on this topic. So it can have the facet of if you have a new technology, where is the best place to do the initial innovation? Oftentimes it's here in US. Where is the place you can do most efficient R&D? Oftentimes it's also here. But where is a place you can do pilot scale manufacturing? A lot of times it's not here. So can you utilize the global resources to do that? That's one aspect of that. The second one is the market, like Delia said, this certain technology is easier to implement it in certain region of the world. So that needs to be considered. There's also the access of capitals. and where you have the best access of capitals for certain technology, it's different for different countries.
Yeah.
At the end, it's also the energy resources available are highly imbalanced. The place use most energy oftentimes don't have energy, that much energy, right? Whether it's the sun, whether it's wind, right? Whether it's oil. So how do you connect the global energy net in a very efficient way? I think that requires some thinking with this technology of high transmission line, high voltage transmission line go to 2,000 kilometers. You can make chemical fuel, you can ship those chemical fuel to different regions. This requires new thinking to capture this opportunity.
Let's take some questions from the audience. You've got a row of experts. Let's start right there, and then we're going to go right there. Oh, sure. Yep. Here we go. Oh, I was going a little farther up. There you go.
I'll be quick. So hi, my name's Tane Danger. I'm from Minnesota, and I wanted to ask on behalf of the farmers in my state if biofuels are already over.
So I would say that biofuels represent a means to produce liquid fuels by a renewable cycle at the moment. We do not currently have an artificial photosynthesis industry anywhere in the world, in the United States or anywhere else. Some of us are working very hard to bring that about because fundamentally it's an inherently much more efficient. In fact, at Caltech we were able to recently develop a device that operates 10 times more efficiently than natural photosynthesis. The implication being that in large-scale deployment it could use 10 times smaller land area to perform the same amount of fuel synthesis. So if you look at the imbalance between the need for fuel and the capacity for biofuels to deliver the fuel, there is a significant mismatch. If you look at the entire fuel supply of the entire US vehicle fleet, about 160 billion gallons of fuel, we can't meet that with the available land, arable land capacity of the United States. So there is a mismatch. So we need another solution. It is important as a partial solution. It's the one solution we now know for making renewable fuels.
Also, a lot of the more advanced technologies, what were supposed to be sort of like next generation biofuels, in the way that scientists and technologists have beat the targets on solar, they've missed the targets for advanced biofuels by like wide margins. A lot of things, when I was first reporting about green technology in 2007, 2008, there was tremendous optimism and lots of venture capital flowing into all kinds of different biofuel companies, some of which were working with algae, figuring they could reprogram the algae to just like output oil, some of them working with ways of like breaking down the cellulose in plants to make ethanol production more efficient. And as it's turned out, like most of those things, as they went to scale up, just like didn't make the cut. And so I don't know if it's over, but it's certainly at a low point, it seems to me, in terms of like the interest. I apologize to any biofuels investors or company owners, but it just doesn't, there have not been the same like success stories that you've seen in some other areas of green technology.
Can I add here? So in my opinion, as Harry also said, that there's not a single solution. So we need all of these options to solve these issues. And for example, what comes to biomass, I think it's in the palette of the sources of energy, and it varies a lot from country to country. And I come from Finland, and there, biofuels and biomass is a really big issue at the moment. And then, for example, in northern countries, if you go to Denmark, they have lots of wind energy, and that just varies from country to country too.
Yeah, and like using just to a waste stream like the gas, like the stuff that comes out of the sugarcane fields to turn into fuel. Like people have done that, and it has worked decently well. Oh, I was going to go right there.
Certainly. Leisha John, EY Sustainability. My question is about the circular economy and how that's affecting materials science. If you could talk a little bit about that. Mike, I think you implied something with your comment on sand.
Could you please repeat the question? I didn't.
I'm curious about the circular economy and restorative design and how that's impacting material science.
So full life cycles for manufacturing of materials-intensive products. Yeah. So anybody want to?
What could I say?
So I can mention, for example, in the area of solar energy, this very rapidly expanding business now. It's the largest optoelectronics industry in the world at the moment, just surpassed the flat panel display industry, and continues to grow. We don't want to have 20 years from now a situation where you have waste, photovoltaic panels piled up in a big pile somewhere in Arizona. We have to find a way to remanufacture those. And in fact, one company, First Solar, has already built into the final cost, the entire cost model for the solar panels that they sell you, the remanufacturing and the reprocessing of the materials. And I think that's a trend that's going to be followed and adopted by all of the solar manufacturers. I think there are examples in other industries.
No, well, I had some time to think, so. I think it's we need to consider this issue in all the applications. For example, in power plants, when we burn, for example, biofuel or fossil fuel, we get ash from the inorganic material is left over, and at least in Finland, the legal system or the rules are getting really tight, and if we want to transport this ash to landfills, the prices are going really high. So it's also nice so that the governments are forcing us to think different solutions for these so-called waste materials. So
Yeah.
I think there's a lot of unsung success stories around this too. I mean, I think, the group of green people that I came up with, a lot of them went into companies and just have been working away, grinding away on we're gonna take this waste stream and make it not a waste stream, and we're gonna use this material which isn't made from virgin plants, and all these other kinds of things that have happened. But they're kind of little, and they're deep inside companies, and so I think they don't oftentimes.
They're not as visible.
They're not as visible. But I do think it's one of the main areas where a lot of the interest in green stuff that flowered in the kind of middle of the last decade, that's where it went. The people, the energy, and the ideas went into the companies and have been changing them from the inside out.
Yeah, I could still add something. So, for example, good example is car industry. And these car manufacturers, if you take a single car, I think it's 99% something, they are recycling of the materials. So that's, in my opinion, an excellent example how this can be done if they put effort on that.
So batteries too now. So your lithium-ion batteries, right? The valuable stuff are recycled. That's your positive electron lithium cobalt oxide. Cobalt is expensive. Take cobalt out. Take lithium out, and there's a copper foil in there. Take out the copper. So the valuable stuff are recycled.
Somebody over here. How about right here?
I'm wondering what the theoretical limit is to how much energy we can get from solar, how that compares to where we are now in terms of world consumption, and how close to the sort of limit of efficiency we are with solar at this point. And not to be too cynical, just I get a little suspicious, and I'm not applying this to you when I hear things that's like Lewis Strauss with nuclear energy saying, too cheap to meter. So I just want to get a sense of how close we are to those limits. Thanks.
So maybe I can field that one. So in terms of the abundance, if you were to take off from the Earth and look back at the Earth, the largest source of energy flux to the Earth is solar. You compare all the other, it's the only primary source of energy that generates all of our other sources. If we were to devote some significant fraction of the land area, something like 50% of the land area, we could make hundreds of thousands of terawatts of solar electricity. We only, as a human species, consume 18 to 20 terawatts. So it is easily the scale at which we could produce, just based on limits of land, solar flux, and so forth, those essentially are not limits. There are limits to materials, and you mentioned that there are always inevitably costs. I portrayed a scenario where the cost will go down and possibly dramatically below where people thought it would go a few years ago. It's never going to be free. It's never going to be too cheap to meter. But there is a tremendous opportunity. In terms of efficiency, the current solar panels that you buy from SolarCity or Sungevity or something, solar installer, are typically in the range of about 17 to 20% efficient. So our company, Alta Devices, developed the world record one-sun solar cell at 28.8%. If you now use multiple materials, you can bring the efficiency up to about 44 or 45%. We have a project in the lab to go over 50 at the moment. So I think we haven't seen the end of efficiency. And for the reasons that Alexis talked about, when you buy a solar system, there are all these other costs, the costs of installation, permitting, the land, and so forth. Those are now more than the cost of the solar panel itself. And so if you raise the efficiency, you lower all of those costs. So there's a lot of headroom for efficiency. And so I think that's the story, that we're at about half of what will end up, I think, being the feasible limit in efficiency at the moment.
I think one of the things that's really interesting about solar installations right now, though, is I think, at least in the utopian scenario, it was all going to be rooftops, wouldn't take up any new land. But a lot of the installations of solar that have gone in the U.S. at least have been like ground-based utility stuff. So it's just like taking some land and you put a bunch of panels on it. Do you see that changing, or do you see that continuing, that most of the scale for solar comes from utilities, just like putting in big solar fields?
So that actually is driven more by the project financing. It's actually not, so for example, there were favorable terms offered by PG&E and Southern California Edison in California to build these very large solar installations that people are taking pictures of, square miles, for example, in San Luis Obispo County in California. If you took the same solar manufacturers and same project financiers today and asked them, would they do that again? Many of them would try to build smaller, maybe 1 to 30 megawatt installations closer to urban areas so that you don't have to pay as much of a grid interconnection. You don't have to build out the grid interconnection infrastructure to bring the electricity to where the consumers are. And also, one of the fastest growing areas, at least in California, is the rooftop market. So I think it's changing over time.
Yeah, interesting. Let's go, we got one right there, and then we'll go over here.
Thanks. Question, I heard years ago about some kind of a solar, maybe a sail or something that they would have in the atmosphere, and that way we could gather the sunlight 24 hours a day, and it could be this massive device. Is that something that they're still talking about? Is that even real? Is that something that was in the talks?
People have proposed things like that, for sure. Yeah.
So
space-based solar is definitely something that people have suggested, and then like beaming it down with microwaves, I think is what it generally is, like down onto the Earth. It's my second favorite solar solution to moon-based solar, and then like building a moon. I mean, it's just as a fun technology. But anyway, sorry.
I don't know how much you can gain right there. So the solar flux coming in, we pretty much know how much energy you have per meter square, right? It's 1,000 watt roughly per meter square. Then you need to have large enough surface coverage in order to harvest that energy. So I'm not sure.
Well, and in terms of transmission, it goes exactly the opposite direction of what Harry just mentioned, where you're making the transmission problem a huge challenge in that case, right? So we've created a new technological challenge. So I at least personally don't know anyone who's actively working on it, even if there are some theoretical benefits.
There's some work related to that with regards to, you could say that throughout the air, there's sort of radio waves going along a long time, and those are a form of energy. So one of the difficulties though with beaming energy down is that you have to kind of process it and turn it into useful energy, right? You have to do some sort of rectification and things, and then without getting into what rectification is, it's very difficult to do that efficiently. Right, so if we start with the proposal that we're going to put a collection agent in space and then wirelessly transmit that energy, you don't want the energy to spread out. You want it to be very focused, which means now your targeting has to be unbelievably accurate, right? Over thousands of miles, it's like trying to hit a stop sign from, in Boston from here, And then when it gets to there, you have to, find some new device for rectifying it. It's a tantalizing problem, and the reason it keeps coming up is it just seems like the perfect solution, but we don't know how to do some of those things yet.
Also, I think the other reason it keeps coming up is that, when people were first starting to think about solar power, it was a time when like space as a research agenda for the United States was like dominating the R&D spend. So if you were someone who wanted to work on something that was not space, you would be like, but you could do it in space. And then I'm totally serious. This is like how a lot of how it works. So even people doing biomedical research would be like, well, I really want to like study the heart in space, and then that's how they would get the grant money. Let's go right here.
My name's Robert Potter. I'd like to follow your 5-megawatt picture that you described before and attempt to turn it into a big idea in the spirit of the Ideas Festival. And that is to say, previously we identified storage as a key energy problem. Well, we could revolutionize the mobile transportation, the car industry, and solve a bit of the carbon problem by building a new way to store electricity, and I don't want to call it a battery, but a new way to store electricity that meets the parameters that you described. Be able to recharge in 5 minutes and go 200 miles. I would submit that there's no university or company that has the capability and the finances to develop that whole new way to store electricity. It's not one of the current, all the battery developments are evolutionary. This calls for a profoundly different way in the spirit of John Kennedy saying, I want to send a man to the moon and return him safely by the end of the decade. Nobody knew how to do that. 2-stage rocket, 3-stage rocket. And if the federal government would launch a program of that magnitude, it could solve any number of these problems and make transportation far more efficient. The government has done that 2 times, the Apollo project and the Manhattan project, where they got the best minds, all 6 of you working on it. And
I'd just be a PR guy, actually, in that scenario.
Say it again, please. You'd be in. And I would submit that that's the kind of target that is sensible for government. Do you agree?
So your question is actually very timely and germane because the government actually, in the form of one of the energy innovation hubs, has actually launched a large research project on next generation batteries. It's called the Joint Center for Electricity Storage, J. Caesar, and it's centered at Argonne National Laboratories. And they're working on sort of moonshot type approaches to building next generation batteries. These are things that Yi thinks may not work, so that's how risky they are. But the government is doing them anyway. So you'll be heartened to know that they're trying to, for example, store 2 charges per ion using divalent ions that, like magnesium, that store 2 charges per atom rather than 1 in lithium, things like that. The chemistry challenges are enormous, but there is an effort.
Well, I thought, and correct me if I'm wrong, but I thought Tesla, the company, had a very kind of mundane solution, at least to the charging problem, which is that they actually had a method of physically swapping out a battery, right? So you just say, well, you shouldn't take charging however long you like. But
That's a company, Project Better Place, did that. Tesla is doing the regular charging.
Oh, okay. All right.
Yeah, but it's hard to get within 30 minutes of charging. It's very hard.
Yeah.
So coming back to that, so you mentioned Manhattan Project. So we need Manhattan Project for energy as well. But remember, this is different. When you produce an atomic bomb, you produce a few. When you produce a battery, you produce 1 billion of them. So there's a cost issue right there. You can produce an atomic bomb without considering the cost. Energy space, costs always come very early on. That's the challenge we need to learn how to deal with. Not only make 1, not only make 2, not only make 10, let's make 1 billion of them a trillion of them. So how do we do that with low cost? University can do that, in the prototyping and the concept demonstration. National lab can do that. Once you go to a billion of them, we need industry, very powerful industry behind it.
I'm going to go right in the orange scarf. Probably be our last question, unfortunately. You've made it through the deep dive.
Hi, my name is Deepa Javeri. I'm curious about the intersection between academic innovation and research and commercial success and application. Could each of you talk a little bit about how your institutions of higher learning supported you in the journey, starting with the intellectual property protection patent process through to the navigating fundraising and venture capital, potentially all the way through to running your businesses? If you could help us understand how they supported you, and more importantly, I'd love to hear how they could all do better.
Because you all have companies. Yeah, okay,
Yeah.
sure.
I'll start on that. First, let me just say I think it's incredibly important and essential to any of this innovation that it starts, everything that you've heard about has started with fundamentally new science and new discoveries that requires academic or national lab support, requires government investment. The financial outcome is far too uncertain to do any of these things from nothing with industry and venture investment. At least that's been true of everything you've heard about here. And then the transition from those discoveries and proof of principles into the commercial realm is something, I was very fortunate to be at Lawrence Berkeley National Lab when we first developed our technology, and to receive support from them in just introductions and networking, support in the initial stages of launching a company, and to leverage a network of people who had done it before me and had bridged that gap. So that's, I guess, I'll stop there and let other people share their stories.
Yeah, I think for so our story is that started out in my research lab at MIT and came out, and so one of the ways that MIT supported that was they paid for the initial patenting of the idea when we had it, and then it was a very generous licensing deal. So we had an exclusive license. They didn't just sort of run and auction it off to the highest bidder before we could get started. So that was. I would say that with MIT in particular, but with a lot of the institutions here, probably the biggest boost is the networking and the brand name, right? MIT is a tremendously powerful brand name. When I, going to a venture capitalist and say, well, I've got a technology coming out of an MIT lab, right away they just sort of step back and assume the technology is going to work, and then they go and say, well, you're merely an academic, can you run a business? That kind of, but the conversation moves right away from kind of the technical credibility to, are you too much of a softie to actually make money? But I think, in terms of how to do better, one thing I think it's useful for academic institutions to, they should just be sort of clear in their minds, like what they're trying to do with the patents. Are they trying to maximize, the return on investment to the university, or are they trying to kind of reap a return in terms of it looks great for their reputation, to have successful companies coming out, and you do things differently. If you want to return on your investment, you're a very hard negotiator when it comes to the licensing agreements. If you want to just kind of send companies out into the world, then you're very generous, and you can maybe what you do is you say, well, you get very loose with your faculty. Spend 2 or 3 years trying to get this off the ground, and then come back, that kind of thing. So I'm not sort of recommending that, but these are the things that I don't think have been sort of thought through at a lot of the institutions that I've seen.
So one of the things I'll just mention at Caltech, I agree with all the things that Delia and Joel said, but one additional piece is that our intellectual property office is very flexible, customized terms for almost every transaction. Plus, in the case of a startup, startups are usually cash poor and idea rich. And of course, intellectual property, maintaining exclusive licenses and maintaining patents is relatively expensive to a startup. So they offered a deal to many startups to take a very small equity position in exchange for deferring the cash. And so there are downstream royalties, but no cash out of the startup.
So I think based on what they already said, let me add a few thoughts. This is a learning curve through my startup company Amprius, a battery technology startup. So my investor, John Doe, is actually sitting right there. So he can see part of that. So, so at Stanford, right, they are certainly getting the IP licensing and raising venture capital is straightforward in Silicon Valley. It's not as straightforward as before now, because clean tech, VC investment really they didn't do that well. There's one thing I learned though. You need to recognize the energy technology. Particularly, you go down to the level, the closer you are to the atoms or molecule, the longer it's going to take to get to commercialization. We are speaking about easily 20 years, 15, 20 years, right? You look at all the past technology, easily 15, 20 years. So you say, well, I raised my VC funding. If VC can give me 5 years, how do I get there? Looks like it should be 15 years. If you're lucky, you're smart, you can get within 10 years. So I think this really made me think, how do you finance your technology? Not necessarily through startup, but you need to accumulate long enough. For example, you go to National Science Foundation, Department of Energy. Within Department of Energy, there's a different agency within that. So if you can build up that funding profile for that technology, that idea, for 7 to 8 years, adding VC's funding for another 5 years, you might get there. This is my rough calculation, you might get there. So over the years for Amprius, so we are lucky in a sense, I keep having money coming in through Stanford University, through funding agency, whether it's a DOE, whether it's from Saudi Arabia, King Abdullah University. This add up together, roughly cover my 8 years, plus the VC funding together. I think it's very healthy dose at different time to develop that technology. For the future of the technology I want to go through that pattern as well. So you want to have enough of understanding, R&D, within university first to de-risk that technology before you move on to VC funding.
Right. Anything to add from
well, I could try to add something. So we are just building up the company, but I think that it's totally two different things to make science and to make business. So, for example, in Aalto University in Finland, we have this center of entrepreneurship. So we want to remain as scientists, and then we are very fortunate to have help on putting the process commercial. So there's really expert on economics and things like that, financing, to support us, so we can focus our core knowledge, and then we get the support for this economical part. So
cool.
That's, but no experiences yet on the.
Well, thank you all for joining us. I hope you learned a lot during this deep dive. Thank you.